Hi, I'm Mr. Franklin, and in this video, we're going to take a look at basically our ants on a slant number 5 and how using a ramp can help lift an object. And we're going to talk about it in terms of net force. We're going to try to keep it conceptual. We're not going to do really any of the math. First thing we need to recognize and review is, first off, is we have an object sitting on the ground and we want to lift it. So we want to take it and we want to lift it up to some height. How are we going to lift it? Well, first, to lift it, basically you have to be able to pick it up. Well, how much force do you need to pick it up? You have to at least pick it up with the weight of the object. You have to be able to lift with the weight of the object in order to lift it to the height that you want to lift it to. But then we can take and we can put the object on a ramp. And as we saw in our ants on a slant gizmo, if we put it on a ramp, we can actually lift it. If it's a really shallow ramp, we can lift it much easier. If it's on a steep ramp, it can be very difficult to lift. If it's straight up and down, it's like lifting it straight up, okay? So let's talk first, before we go any further, just a quick review about what the normal force is. So when we have an object sitting on the ground, for every force, there's an equal and opposite force. So the force of gravity is pushing the box down. So the box is actually pushing on the ground here. Well, if the box pushes on the ground, well, the ground is actually pushing back on the box. And that's the normal force. So this arrow that's pointing up right here is the reaction force, because the box is pushing on the ground, but the ground pushes back. So the force and weight are exactly equal. So when we set it on the ground and we leave it alone, it just sits on the ground. It doesn't go up into the air, doesn't slide left, doesn't slide right, because the net force equals 0. So Newton's first law is telling us the object's going to remain stationary. Okay, so now what happens though when we take this ramp and we are going to raise the ramp? Watch the normal force. Watch what happens. See how the normal force gets smaller and smaller, and then there's 0 normal force. Why is there no normal force? Well, it's not pushing on the ramp anymore. It's going to fall straight down. So let's take a look at it right here. So the normal force, it's called the normal because normal means perpendicular. So the normal force is a reaction force. So the weight of the object is pushing against the ramp and the ramp is pushing back. So that amount of force is the normal force. Well, it's equal and opposite to this force. Well, this force is what's called a component of the weight of the object. So let's take a look and go back and take a look at this weight. Okay, so weight, if we look at the entire range of movement of the ramp, notice this, see this little 2 lines here on this arrow? Notice that arrow never changes its size. That arrow always points downward because that's the actual force of gravity. It's always pulling straight towards the center of the earth, which for us would be down, and it doesn't change. So that's the actual weight of the object. Now, what we can do though, especially because we're dealing with angles and things, is we can take this force and we can split it into pieces. We can use basically a Pythagorean theorem and some other things, and we can take this weight that we have here and we can split it into its components. Okay, so we could do this with any vector. So I can take something like this, and if I'm traveling at an angle like this, I could measure out a distance traveled going straight up and a distance traveled going to the left. Okay, and we could find out that that's the actual result. Okay, so I'm kind of doing it a little bit backwards here, but we're not trying to get too much into the math. But you can see that if I take these components, I could measure this off and then measure this off, and if I add those together, it would result in this. Okay, so watch this. So this little leg of the triangle, we actually have drawn through the center of the box, and it's pointing parallel to the ramp. Okay, so we got a force of the weight, a part of the weight that's perpendicular to the ramp, and we got part of the weight that is parallel to the ramp. Now watch what happens when I change the ramp here. So notice what happens down here. The parallel portion is really tiny, but the perpendicular portion is almost the same length as the regular weight of the object, the actual weight of the object. When I raise the ramp, okay, way up here, you can see that the perpendicular portion is really tiny and the parallel portion is really large. Okay. And so you can see how that changes. And so when it's flat, the perpendicular portion is exactly equal to the actual weight. And then when it's perfectly like this, the parallel portion is exactly equal to the weight. Okay, so this angle actually causes those portions of the weight to change because it's basically causing a change in the direction the weight is acting. Okay, so notice this too though. So right here, put this in the right spot. So notice that the normal force, the size of the normal force is exactly equal to the perpendicular portion of the weight. So we get up here, the normal force is tiny, but it's exactly equal to the perpendicular portion of the weight. We go down here and the normal force is much larger, but it is perpendicular to the, or it is equal to the perpendicular force of weight. Okay, so now let's go back to the question in the gizmo. We are trying to lift this box up. So which type of ramp, I already said it once, but which type of ramp actually allows us to lift the box with the least amount of force? Okay, it's the shallow. So if it's shallow, I require less force to push the box up the ramp. Why is that? Okay, well, look at this. I'm pushing against, when I'm sitting here and I'm pushing against this, here, I'm going to change the color here. When I'm pushing the box up the ramp, what am I actually pushing against? Here, I'm pushing against the parallel force. If I go here, what am I pushing against? I'm pushing against the parallel force. Okay, so to lift it, I have to at least be equal to that force. If I push greater than that, okay, I'm going to get an acceleration going up the ramp. Okay, because net force, if it's positive, it's going to cause an acceleration, right? Okay. But the minimum would have to be almost exactly equal to that. So when I get straight up and down, the parallel force and the weight are the same. So what am I pushing against? I have to lift against the entire weight. Okay. So the ramp helps us because I'm pushing against the parallel direction of the weight. And so it's easier to push. But notice, why am I actually able to do that? It's because basically the normal force is holding the other part of the weight. The normal force is pushing up again in the opposite direction, okay, of this perpendicular component of the weight. And so the ramp is actually helping us hold the weight of the object. So as we go up, notice that the perpendicular weight is less. So the perpendicular portion here is less and less. It's getting smaller and smaller as we go. Steeper ramp. That perpendicular portion is smaller. So in a sense, the ramp is holding less of the weight. Okay. And so we would have to push really hard to get it up this ramp. Whereas if we lower the ramp, the normal force is actually helping us push against the weight, hold the weight while we push against the small part of the weight. So basically a ramp is causing the weight of the object to be split into two components. I won't say X and Y. It's a parallel and perpendicular to the ramp, and it allows us to lift the box easier. Now, one of the things you got to notice, a shallower ramp has a drawback to it, and it is the distance that's used. If you've ever looked at a wheelchair ramp, those are usually really, really long. Okay, I don't know if you've ever had to use a wheelchair and push it up a ramp, but you don't want to have to expend a lot of force trying to get yourself up the ramp. So we need the ramp to be shallow, but to make it shallow and go up a steep hill, we got to make a long ramp. So I know sometimes as a kid and not in a wheelchair, I've gone through, and you can see that you're kind of doing it for fun, but it takes you forever because you're running back and forth and back and forth and back and forth. Well, they're doing that because they're making the ramp shallow so that someone can push just against that small parallel portion of the weight, and they can manage to get up to the height that they need to get to access the building or whatever it is they're trying to get to. All righty. So that is a crash course on the ants on a slant problem with lifting a box using a ramp. It is totally conceptual. If you would like a more mathematical explanation, you could come see me during tutorial. But that's all I've got. Thank you and have a good night.